Now, starting from case 2, let's consider case 3, a general case. Well, in this case, we just consider a sample section. Okay. Let's consider a simple section. Okay, here let's consider a beam segment. Consider a beam segment subjected to M on the left and M plus delta M on the right. Okay, then this is the neutral axis. And the cross section of this beam section, the cross section is a rectangle. And this is centroid, easy to find, right? And the neutral axis is going through this centroid. Then let's consider a random point. Let's see a random point. Okay. This is a random point at which the tau is to be calculated. Okay. So we will have this area, and you will have a local centroid, right? And here is the D, right? Then we'll have the dimensions of the cross section. Here is B, and the depth is H, and we count everything from the top surface. And let's see this location of the random point where the tau is to be calculated. The location is Y. Okay, and from here to the centroid, this is the Y bar. Okay, those are the dimensions of the cross section. So based on this, we can calculate the delta F and Q and then tau, right? This is based on the equation we just derived. So here the delta F can be calculated as delta M by Q over I, right? Where the Q equals AD. Right, so the tau is calculated as delta F over interfacial area. Interface area, then this can be extended as delta M by Q over I over, and what is the area? The area of the interface. The area of interface as denoted here. So if we give you that the length of the beam segment is delta X, so the area of the interface will be delta X by B, right? Here is the B. Rearrange this equation, you will get delta M over delta X by Q over IB, right? So now let's check this term. What is this term? What is this term? It just It's just dm over dx, right? The derivative of a bending moment. What is the derivative of a bending moment? Is that slope? Is that shear? Right? From the integration method, you should be familiar with this whole integration process or derivative process, right? This is the first derivative of m equals v, right? So this equation can be rewritten as tau equals vq over ib. So in this equation, you can examine all of them, all of these items, all of these parameters. Okay, let's see Q. Let's see V first. And the V is the shear force. So in a loaded beam at a random point, at a random cross section, the V is a constant, right? The overall V is a constant. Well, you can read it from the V diagram. Okay, the I, of course, is a constant, and the B is also a constant. So the Q in this equation is the only variable. It's the only variable. So the variation of Q determines the variation of tau. Okay. So later we can examine the directions of the tau, the shear stress. Okay. Then if you look at this beam section, look at the beam section, the beam segment. So if here is the neutral axis, above the neutral axis, the force will be in compression. And below it will be in tension. Right? So above the neutral line, since the force on the right-hand side is always larger than the left-hand side, right? So above the neutral axis, the equivalent force will be F1, and on the right is F1 plus delta F1. So the direction of the force will be pointing left. So the direction of the tau or the V will be pointing right. Right. So below the line, below the neutral axis, this is F2 and F2 plus delta F2. So the resultant force will be pointing right. So to balance it, the shear generated will be pointing left. Right. So this is the difference. So based on this analysis, we can examine the values of the tau. Since we mentioned that the tau, we just derived the tau equals VQ over IT, and in here the Q is the only variable, right? This the Q equals A by D, right? And the A look at the figure here. What is the A? The green colored area. What is the area? It's B by Y, right? It's determined by the location, Y, where we're determining the shear force, the shear stress. Right? So the area equals B by Y. And what is D? D is Y bar minus, look at here, what is the location of the local centroid? The location of the overall centroid is Y bar, and the position of the local centroid of the green area will be Y over 2, right? So here is the Y bar minus Y over 2. You rearrange it, you will get by bar by Y minus B over 2 Y squared. Okay. Having this equation, we can examine the Q values at different locations. Okay. If the Y equals 0, at Y equals 0, the Q equals by bar 0 minus B over 2 0 squared, so it's 0. Okay. Then how about at Y equals Y bar? When Y equals Y bar, the green area will be half of the overall cross section. Right? It's the line Y is passing through the centroid, the overall centroid. So when Y equals Y bar, it's in the middle. Right? Then the Q can be calculated as B Y bar square minus B over 2 Y bar square. So this is B over 2 Y bar square. Noting that in this figure, the Y bar actually equals half H. Right? So we just substitute the half H here. So this Q equals B over 2 by H over 2 square. So this equals BH square over 8. Right? Then how about at Y equals H, or 2 times Y bar? That is at the bottom. Right? At the bottom. Then here is based on the equation, the Q equals B Y bar by 2 Y bar minus B over 2 Y bar square. This will be 0 again. Okay. So look at here. On the top, you get 0. In the middle, you get a number. And the bottom, you get another 0. Okay. Since the Q is the only variable in this equation determining the shear stress, so actually the shear stress also equals 0 on the top, equals 0 at the bottom, then it achieves its maximum value in the middle and passing through the overall centroid, the global centroid. So if we have this beam segment, and here is the neutral axis, right? So the distribution, this is the neutral axis, the distribution of the shear stress will be like this. Right. So it's 0 on the top, 0 at the bottom, and it reaches its maximum value in the middle, where the Q equals, this is tau max, where Q equals BH square over 8. Okay. So this will be this will be the equations we derived, and later you will see them again. So when you see them again, you should just recall this whole process and to try to understand how did we derive them and what is the mechanisms behind them. Okay, so after this, it will be very interesting comparing the distribution of the bending stress and the shear stress along the direction of the depth of a beam segment. Okay, let's do this comparison here. This is the beam segment again. The beam segment again, the same as here. Okay, and you have the neutral axis, and you have bending moment applied on it, and this is delta x. So if this is the case, what is the distribution? Let's draw the distribution of bending stress and the distribution of the shear stress. Okay, so what is the distribution of the bending stress? If this is the bending moment, according to the bending moment shown here, on the section on the part above the neutral axis, the beam section will be subjected to compression, and below it will be subjected to tension. Right, so the distribution will be maximum value on the top, compression, maximum value of tension on the bottom. So the distribution will be like this. Right, this we assume the linear distribution. Right, then the distribution of tau, as we just analyzed, it will be 0, 0, maximum value as the neutral axis. Right. Now here you have 0 value and maximum compression, maximum tension. Okay, you can see that at the locations where you have the maximum normal stress, like the bottom and top, right, you have 0 shear stress. The where you have 0 normal stress at the global centroid, so you have the maximum shear stress. Okay, this is the interesting comparison between the two types of stresses.